All right, let's discuss this chapter 2.3, electric potential. So you know potentials, volts. You may think you understand potential, but that's what we're going to discuss right now. So electric field, the key thing about an electric field lines never cross. So that means the electric field never has a curl. Okay, so curl is always 0. So if you do del cross E, you get 0 every time. Otherwise, it can't be an electric field. So that's an important thing. What that leads to is the line integral from A back to A is always 0. A closed loop is always 0. That integral is always 0. So then we can define a new thing, which is the integral of an electric field dotted into the path from, let's say, A to some point B. Okay, but it's the electric field dotted into the path. So if we imagine an electric field like this, and we travel along this curved line, we're only taking the component that's along the line to calculate this function, E dot dl. Okay, that is called the electric potential. It's the integral of the electric field along a line. So point charge, electric field, okay, E dot dl, integrate from 0 out to some r, and then that will give you the total amount of electric field you've waded through, and that's what this integral is called. The difference of once you get your function of the potential at b minus a is just the integral from a to b of E dot dl. So what this means is, okay, this is pretty cool. The fundamental theorem for gradients says that the function evaluated from b minus to a is equal to the gradient of the function. This is just the fundamental theorem of calculus again. So if this is the case, and that is the case, and this is that, and that is this, then we have this equation here, which says that the gradient of this potential is equal to the integral of the electric field. Now, since this is true for any point A and B, that means that this has to equal that, okay? And so you end up with, this has to equal that. I looped in the deal there. Okay, and so there is our next equation, our next big equation, that you can write the electric field as the scalar, the gradient of a scalar, which is kind of crazy. You can write the vector as the derivative of a scalar. Okay, that's kind of crazy, right? He's got this little aside here, which is whatever, notational stuff. Okay, so this is a little bit crazy. Okay, and then problem 2.2, you're going to have to do this one. Just says one of these is an impossible electrostatic field. So just do del cross E on each of these. Whichever one is not 0, it's not an electric field. Okay, so the electric field is a special thing. Since del cross E is 0, then you have this special thing. So the electric field is a special kind of vector. That's what makes the electric field the electric field. It's pretty cool because you can turn a vector problem to a scalar one, in which there's no need to fuss with any of the components. So that's pretty cool. Now, when you're trying to determine the potential, usually we use a reference point. So he goes off into this thing talking about sea level. Okay, if you want to talk about, how high Denver is, okay, you'll say 5,000 feet. It's a mile-high city, right? Mile high above what? Sea level, okay? Why? Because that's convenient. That's what we generally talk about. But you could say, what is it with respect to the plains of Iowa or whatever. The idea is you need a reference point to determine the altitude or whatever. So when we're talking about voltage, we're talking about what the voltage is relative to a point. So you've got your electric field, okay? If I ask what's the voltage here, that doesn't really make a lot of sense unless I say what's the potential here with respect to this point here. Then it's a certain amount of volts from here to there. Okay, what's the potential out here? Well, is it with respect to here, or here to there, or all the way there to there? So you have to have a reference point when you're talking about the voltage potential. Usually on a battery, it's the plus to minus, and so there's your potential differences from those two things, those two areas. In this case, we're talking about the integral of the potential of the electric field vector. Okay, so the reference point we always use for the most part is to set the potential at infinity to be 0. So that way far away, it's 0, and then as we get closer to a point charge, the potential gets bigger and bigger and bigger. Okay, so that's the idea, is that we set the potential at infinity to be 0. Okay, yep, so then they do an example here of there's a special case where that doesn't work. And that is in the case of the plane, a infinitely flat, charged plane, which is stupid, as he says, because, there is no such thing as a actual infinite charged plane, so you never have to worry about that. But. Okay, so the important thing is that potential obeys the superposition principle. So just like the total force in some charge is just F1 plus F2, and the total electric field is just the sum of all the electric fields generated by all the charges. Same way, the potential also satisfies the same thing. So you can just add up the potentials. Okay, so the unit of potential is the volt. It is a Newton meter per coulomb. Okay, we're integrating the force per charge. Force per Q equals E. And then the integral dl is meters, so you get Newton meters per coulomb, or joules per coulomb, and a joule per coulomb is defined to be a volt. Okay, so question is, find the potential inside and outside of a spherical shell of radius r that carries a uniform surface charge. So it's just a surface charge, some sigma, and say our reference point at infinity is 0. Okay, we know that the electric field is just Q over r squared times 1 over 4 pi epsilon naught Q over r squared. And Q is the total charge on the sphere. Remember, the total charge on the sphere will be 4 pi r squared times the charge, sigma, whatever it is. Okay, and that should be the total charge Q. Okay, so then if we want to figure out what our voltage is outside the sphere at some point where r is bigger than big R, then we do the integral from infinity to r, to the point just above, at some point outside the sphere that has written here. Negative 1 over 4 pi epsilon naught times the integral from infinity to the r, Q over r prime squared dr prime. And then you do this integral, and you get just 1 over 4 pi epsilon naught Q over r. Cool. To find the potential inside the sphere, now we're going to take the integral from infinity to big R, and then from r to little r to calculate what the potential is. So if we do this, we see that the potential is not 0 inside the shell, even though the field is, which is a little bit interesting. V is constant in this region. And that's where you get this del V equals 0. That's what matters. So just make sure that when you're doing these calculations that you're not assuming too much, like you might assume that the potential is 0 inside. Not always the case. Let the math be your guide. Okay? It's because the potential inside the sphere is sensitive to what's going on outside the sphere as well. Okay? And then we've got some problems here that we'll do. And then Poisson's equation and Laplace's equation are just, we know that this is the case. So then the question arises, what does del dot V and del cross E equals 0 do? So since we know that del dot E equals, since we know that E equals del V and we know del dot E, then we say del dot E is equal to del dot minus del V. So this becomes del squared V. So that's where this equation comes from, which says that the second derivative of the scalar potential field is just equal to the charge density. Okay, and that's known as Poisson's equation. In regions where there is no charge, where rho equals 0, Poisson's equation reduces to Laplace's equation, which is when del squared times your vector scalar field equals 0. Okay, so there's your two special cases. When you got a charge, then the second derivative equals the charge density. If you don't have a charge, then it should equal 0 in that region, which we'll get into in chapter 3. Okay, so del cross E is equal to del cross minus del V. That should still equal 0, but that's no condition on V. The curl of gradient is always 0. Of course, we use the curl to show that E could be expressed as the gradient of a scalar. So it's not really surprising that this works out. So del cross E equals 0 permits E equals minus del V. In return, E equals minus del V guarantees that del cross E equals 0. So it only takes one differential equation, Poisson's, up here, to determine V, because V is a scalar. For E, we needed 2, the divergence, and the curl. Okay, so the potential of a localized charge distribution. So let's say you are trying to figure out what the potential looks like for some arbitrary charge distribution instead of point charge Q. So we got to replace our Q with rho. Okay, so now we've got our voltage, we've got our charge density, we've got our E. Those are the main players in the electrostatics. So we know that the electric field is kq over r squared, or 1 over 4 pi epsilon naught q over r squared. Let's see, what are we looking for here? Yeah, so we're saying that our voltage potential is just the integral from some reference point, usually infinity, to r, and then E dot dl, and then you do the integral, and you get 1 over 4 pi epsilon naught q over r. 1 over infinity is 0, and then, q over r, whatever. So you see the advantage of using infinity for the reference point. Kills the lower limit on the integral. And then, yeah, he just goes through this. What he's basically showing is that for any volume charge, the potential is just the integral of the charge density, and then just 1 over r there. Okay, and so that's the equation we're looking for. It tells us how to compute the potential when we know what rho is, and, if you like, the solution to Poisson's equation for a localized charge distribution. Okay, so compare this with the formula for the electric field. Okay, they look pretty much the same, except we've got this dl that removes one of the r's, and so you just have 1 over r. And the unit vector r hat is gone, so there's no need to fuss with the components. The potentials of a line and surface charge simply reduced down to blah. Okay, whatever. It's awesome. Okay. Yep, find the potential uniformly charged sphere. Same thing as we did example 2.7, but now we're going to use the potential equation to do it. So remember our surface charge density, dA, and then what he does here is replace this vector there using the law of cosines to find this point z in terms of r and z here. Okay, and then do the integral on the sphere, r squared sine theta d theta d phi, and you get this integral, and you end up with this on the outside and this on the inside by doing the integral. And total charge of the shell is this. Okay, q 4 pi r squared sigma. This is exactly what we thought it was. So then your total potential greater than r is here, less than r is there. Okay, which is pretty cool. Okay, so this, in this case, this is the point, is that it's easier to get v this way. Okay, so for certain problems it makes sense to do that. Then we get some more problems there. Now the thing is here with your boundary conditions, that's the main thing, is to figure out what you know, what you need to know, and you're gonna just get good at trying to determine which equations you need to know. So what this little triangle of doom is trying to explain poorly is that if you have a voltage potential, you can get So if you know the voltage potential, you can get the charge density by Poisson's equation. If you know the charge density, you can get the potential by integrating over the distribution. If you know the charge, you can get the electric field by integrating. If you know the electric field, you can get the charge density by taking some derivatives and curls. If you know the electric field, you can get the potential by doing the integral of the electric field along the line, the path, or if you know the voltage, you can get the electric field by taking the gradient of it. So this is kind of amazing, this wonderful relation between all the different, the main players, the electric field, the voltage, and the charge, okay? The potential, not the voltage. Well, voltage, but whatever. Okay, so then he goes through these examples of your boundary conditions, and we'll talk more about that in the next lecture. But the main thing here is, for example, we don't take the edges of the box for the flux. We only consider the flux through the area at the top. And then we know that tangential components of E, right, are always 0. And yeah, that's pretty cool. So you do a little loop around there. In this case, so what he's doing is imagining this to be just a tiny little epsilon thickness just above and just below, trying to imagine what it would be like if you're a little tiny ant walking around. What would your result be? Okay, and so read through this. It's actually really cool. Yeah. So these boundary conditions relate the fields and potentials just above and just below the surface. So you can make things, force your problem to be certain cases just above and just below the surface. And that sets what happens at the boundary across the thing. When you say coming from the top has to be this way, coming from the bottom has to be this way, boom, that's called your boundary conditions. And then you have the result by approaching it from one side and the other side and forcing it to have those values at the boundary above and below. So that's pretty cool. So that's what this is all about here. Okay, I'll see you guys later. Bye.